Okay, so today we are going to start a new chapter, chapter 9, which we are going to spend a couple of weeks to maybe 3 weeks. So it's one of the important chapters of this book, and it's about statistical inference. We are going to learn hypothesis testing, confidence intervals, how to estimate the parameters of distribution. So this is the plan for today. And before we start, do you have any questions about midterm exam? Do you have any? I'm not going to go over the entire midterm exam and go over the solutions, but if you have any particular questions that you want the answers, I will be happy to go discuss the solutions of some of these questions. Uh, you can also send me an email if you have any doubts about the solutions of any midterm question. Please feel free to email me, and I will also send by email the solution sketch. Um, okay. So next week we are going to have the spring break. So we are going to have a 1 week gap in our classes, but that's okay. It will be a breathing time for you. So you will. We're not going to give any assignments. Uh, okay. Some sounds. So yeah, my USB is recognizing certain things. Okay, so we're also not going to give you any assignments or quizzes during the spring break. Okay, so as I said, in terms of this class, it's really going to be a break in this semester. All right, so so let's start with statistical inference then. Let me also start the book. I forgot to get the book's PDF somewhere here. All right. So now we are starting this one. I just want to go over what we're going to see. We are going to skip section 9.5. We are not going to talk about inference about variances, but we're going to cover the first 4 sections of this chapter, which today we are going to start with parameter estimation. We are going to learn 2 methods, method of moments and method of maximum likelihood. Maximum likelihood requires lots of the analytical solution for maximum likelihood requires lots of mathematics, calculus. You need to take derivatives of some complex functions. So I'm just going to mention the method and solve an easy example from the book. But in general, uh, the finding the analytical solutions may not be very easy, and most of the time we use existing tools like in Octave Online. There are maximum likelihood estimator that you can use directly. So these methods are actually implemented in statistical packages. So most of the time you just either whether it's method of moments or method of maximum likelihood, you usually call those functions and use them as black boxes. But it's also good what's in the background, how these methods work. So the purpose of this section is to teach you the background of these methods, how they work, and what they try to solve, what is the goal. And then you're going to see how do we estimate standard errors, which is the standard deviation of our estimation. When we estimate something, what is its standard deviation? How good we can estimate it? I mean, based on our sample size, we are going to talk about the standard deviation of our estimators. Then we are going to start talking about confidence intervals, which means that with certain probability, we are going to, instead of having a fixed estimator, we are going to build an interval symmetrically around our estimator, left and right. We are going to, so for example, based on the data, we are going to, let me write here. So based on the data, if this is the x-axis for our, if this is the axis for our estimator, And each time we estimate it, for example, we find something here. The next time we take a sample from the population, the estimator can be this point. So the points may be different each time, right? Each time this is a random variable itself. So with confidence intervals, whatever theta hat we compute, we are going to actually say that by looking at a standard error, by estimating its standard error, we'll be able to say that we'll be able to extend this to an interval like this, which we call confidence interval, because we'll be able to tell this with some confidence. We're, for example, going to be able to say that with 0.95 probability, the actual theta, so this is theta hat, with 0.95 probability, the actual, this interval covers this interval, this interval contains the actual theta. I was actually I hesitated when I was stating that sentence because when I say with 0.95 probability, the actual parameter is inside this interval, it seems like it's the same thing, but the actual parameter is not a random variable. It cannot go here and here. It doesn't change. It has a fixed position. So the actual theta may be somewhere here, okay, but it's in a fixed position. Every time you're taking a new sample, we will be constructing intervals around our estimators. And when we say that the width of this estimator, of course, the interval is of course important, but based on the standard error we compute, we'll be able to extend the interval to left and right based on the standard error. And we will be able to associate a probability to these, because most of the time, if this estimator is asymptotically normal, we'll be able to utilize the central limit theorem, and our standard error will be the standard deviation of this normal distribution. And we know that, for example, in normal distribution, 0.95 of the samples coming from that distribution is within a certain interval. So if this is the normal distribution that we are going to assume, we'll be assuming that 95% of the population is here. So it's probably, this interval therefore covers the actual theta with 0.95 probability. This is also the confidence level that is associated with this. We'll learn this term alpha, which is 1 minus. So alpha 0.05 means that we'll be having confidence intervals with 0.95 probability. But we are going to come to these in detail. So I'm summarizing what we're going to see. So I don't want to go into details. So we'll also try to say, for example, if you want to have an interval of this length, if you want to fix that, then we will also see what sample size you should have, so that the standard error is small enough, which will give you that interval size. Okay, so there's a relationship between sample size and standard error. By using this relationship, we'll be able to have confidence intervals. And we'll have the easiest case is the theta hat, the confidence interval for population mean. Then we are going to start comparing a new problem of when we have two populations. Can we compare these two populations? So we'll be talking about difference between two means, or estimating proportions. So we are going to talk about those, and if the standard deviation of the individual random variables is known, okay, then it's very easy. We'll be using some standard techniques. But with unknown standard deviation of the individual samples, what is the error margin of these individual samples? For example, the unknown standard deviation means that, for example, you're measuring something, but you don't know in what range or what this single measurement is. But sometimes we know that. For example, the population height of people on Earth, the standard deviation is more or less known. So, but for certain cases with unknown standard deviation, we are going to see a new distribution to solve for that, which is like a more conservative normal distribution, which is called student's t distribution. Okay, it's normal distribution. It's actually wider than normal distribution, which means that we know less about the population. So the bell, the curve of the normal distribution cannot be as narrow. Let's widen it. Let's widen the tails. That's what student distribution looks like. We are going to talk about that. And student's t distribution, a fun fact here, it was first proposed to measure the quality of beer in a brewery. I think it was in Guinness Brewery. So in order to have standard beer quality, quality to measure the qualities of these beers that they manufactured, they didn't know the standard deviation in that case. So student was the pseudonym of a statistician. We are going to talk about the details of these also, but yeah, it's from coming from England, Guinness Brewery. Okay, so then we are going to all these confidence intervals, unknown standard deviation. It's also related to hypothesis testing. We will see this. We'll also spend like a week on hypothesis testing. And it's really important to compare the two populations to make hypotheses about population parameters, whether we can, this hypothesis can be rejected or not. We are going to see based on the sample we collect. We are going to talk about these things. So this is a summary of what we're going to be seeing ahead in the next 2-3 weeks of classes. Okay, and we'll have a break in between and the spring break. All right, so let's go ahead and start. We'll first start with method of moments. And your quiz this week, we'll have a quiz on Thursday this week. It's going to be about method of moments. Okay, so yeah, this is also the outline that I went over. The table of contents is the same thing. And we're not going to talk about inference of variances. 9.5 is going to be skipped. So we have seen in chapter 8 actually how we can estimate the population mean with the sample mean. Sample mean was an unbiased, consistent, and asymptotically normal estimate, because it's a summation of some individual variables. It's then divided by that, the size of the sample. But the average is always asymptotically normal due to central limit theorem. And its expected value is the actual parameter. The bias is 0. And so this is how we estimated the population mean. We also had an unbiased estimator for sample population standard or population variance, which was this, the sample variance. If you divide this by n-1, this is the difference between the sample mean and the individual items. That's squared. If you divide it by n-1, then this was needed for an unbiased estimator. So this estimator is also consistent, and since also it's a summation of random variables here, it's also asymptotically normal. So we already know how to estimate very well the population mean and population variance. So if your distribution that you're trying to estimate is normal, I mean, what I mean is that this xi comes from normal distribution by itself, okay, the xi's. The mean and standard deviations are going to be very good estimators for the xi distribution parameters, okay? But what if xi's do not come what if they're not normally distributed? For example, what if these x1 to xn, what if our population, our random variable here, is a Poisson random variable? Or what if it's an exponential random variable? we know what the expected value, the mean and standard deviation of these individual. We estimate them with these. The sample mean and sample standard deviation is used to estimate these individual variables, mean and standard deviation. But what about the distribution parameters lambda? Or if, for example, if xi's are coming from gamma distribution, what about alpha and lambda? Okay, for example, you may say that, okay, if we know the population standard deviation, there are two unknowns, and so what we can do is, if they were gamma, distribution, what we could do was, let me get a new one here. So after you know what mu is, actually we don't call it mu. This is the estimators. If after you know x bar and s as an estimator for mu and standard deviation, since we know in gamma distribution that mu is alpha over lambda, and standard deviation here is it was square root of alpha lambda, right, like this, right? Or if it was the variance, it would be alpha divided by lambda square. So if you estimate these two things and you know that they're already equal to these, then by using the sample standard deviation and sample mean that you have you have found, you may just plug in x bar here. X bar is equal to alpha divided by lambda. The standard deviation s you have found is equal to this, and you have two unknowns, two equations. So you can solve for alpha and lambda with this. Okay, so this is similar to the method of moments that we are going to see next. So if we have two variables like this, we can use this population mean, sorry, the sample mean, the sample mean and the sample standard deviation. And if the sample mean as if the population mean and population standard deviation is also written in terms of these two variables, we'll have two equations, two unknowns, and we'll have what these equations will set this x bar and s to the left hand side of these two equations, two unknowns. We can solve these parameters, but we will have certain problems when we run, for example, into what if this xi's are Poisson? Yeah, we will have error. Exactly, we will have, when we compute these things, the population parameters, they will be also estimation. We will have error in lambda and error in alpha too. So this is, we will be estimating the population alpha and lambda. So what we will be actually computing is lambda head and alpha head. They will be estimators. And for example, we'll see if this is similar to method of moments estimation. So we are going to indicate MoM or MoM, method of moments estimator for alpha, or method of moments estimator for lambda. So they will also be not the correct actual alpha and lambda, while since we estimated them again by using the sample mean and sample standard deviation, they will be our estimates for the random variables distribution parameters. Okay, so they will have error. We will have, and this is the error we have in these parameters. We are going to call them standard errors. The standard error is the deviation. Each time we get a different sample, x bar is going to be different, s is going to be different. So each time you give them into these equations, you'll get a different alpha, different lambda. But yeah, we'll be able to see, since these both x bar and s are asymptotically normal, we'll be able to apply the central limit theorem after we compute the standard error in them. We'll be able to also estimate the standard error in them, and we'll be able to build a confidence interval around these. Okay, this is my alpha hat, but I'm 95% confident that this interval contains the actual alpha. So we'll be able to say that too. But yeah, we'll run into certain problems, or we'll need to make certain decisions when things are. I mean, if we have a distribution which do not have two parameters, we'll run into problems. What if we have a distribution which have four parameters? In that case, uh, two equations will be coming from these sample mean and sample standard deviation, but two equations, four unknowns, it will not be sufficient to solve this. So method of moments actually is a generalization of this example that I gave you here. Method of moments will be a generalization of that to a larger variable. Or also another thing is, if you have less than two variables, like Poisson has only one variable, one parameter, lambda. Okay, now both the uh, expected value and the variance is equal to lambda, right? In Poisson, if I remember correctly, the variance is equal to lambda in Poisson. The mean is also equal to the expected value, is also equal to lambda. Now, which one of these are you going to use? If you compute s squared, which is your variance, should this be your lambda or should this be your lambda? Which one? They may be different, by the way. So they're not, I mean, in Poisson, for example, they are both lambda, but based on the sample you collect, when you compute x bar, it may be different than the variance that you compute for the same sample. So which one is going to be a lambda? You have to decide on that. So these are, as you can see, just using the population mean and variance. These are two things that we have estimated about the population mean and variance. And the mean and variance may contain these population distribution parameters in them. And depending on whether it's one parameter, two parameter, three or four parameters, we may be able to estimate them by just using mean and standard deviation or not. Or we may need to make some decisions saying that in Poisson, for example, I just want to use x bar to estimate lambda. So my lambda hat is going to be x bar. If you may decide on that if you want to have. And this will also be like a method of moments estimator for lambda method of moments. But yeah, in general, we are going to see a way to come up with equations, more than one equation. If there are four parameters, we will now describe what moments are, population moments and sample moments. And these moments are actually a way for you to generate different equations. Okay, for example, there are moments and then there are central moments. So let's start with those. It's basically just the expected value of for example, the expected value of x is our mean. Okay, the population mean. Expected value of x is the population mean, and it's called the first moment of the population. For example, the expected value of x squared will be the second moment of the population. So let's define these actually. Yeah, so this is the same thing that I told you. If we have a Poisson variable, how should we estimate the parameter lambda? Should we use the sample mean, sample variance? Both of them are equal to lambda. So if we have less than one parameter, that's we need to decide on something. Also, if we have more than two parameters in, we haven't seen such a distribution yet, right? We don't have a distribution up to now, a family of distribution with more than two parameters, but it's possible. We may have a certain distribution, family of distribution with more than two variables. Okay, so In the generic methods of estimation, we are going to discuss these two methods in the book. These are really standard, well-established methods, method of moments and method of maximum likelihood. And today my goal is to finish the method of moments technique. And we may maybe start the maximum likelihood. So let's talk about a moment. A population moment is defined as the kth population moment is the expected value of x to the power k. Okay, so this is just something that we define. As I said, I think its main purpose is to give these different equations that are not linearly dependent on each other. So therefore, different powers of x. If you just find the expected value of, for example, the expected value of x to the power k is not equal to mu to the power k. We know that, right? I mean, this is especially if the standard deviation is non-zero, this will never be the case. Okay, so let me write it here. Let me annotate. So in general, expected value of x to the k is not equal to mu to the k. Okay, so it's going to each time. I mean, this is going to be something different because if it was equal to the mu to the k, the variance will always be zero, because the way variance is defined is that we first find the expected value of x squared, and its difference from mu square is our variance. This is how we compute variance, right? If you remember this. So this is different than mu square. So each time we find the expected value of a power, the kth power of our variable, we get something, we get a different thing, which is a new equation that we can use to estimate these different parameters. So this is, in general, the population moment is basically the expected value of the kth power of your random variable. We already know the first population moment is the mean. First population moment is the mean, but it's the general moment. It's a more generic term. For example, the second population moment is the expected value of x squared. When we talked about this thing, what does it mean? I remember you asking intuitively, what does it mean to the expected value of x squared? And I just told you that it's the expected value of the squared value of those variables. It's nothing more than that. And here you now also know another generic term for that expected value of x squared, which is the second moment of the population. A second population moment is the expected value of x squared. You can do the third population moment, the expected value of x cubed, fourth population moment, the expected value of x to the 4. So in general, it's this. And when we compute the sample moment, we just take the kth power of individual items, we sum them up, and we average those in that summation. Okay, so this is the sample moment. As you can see, the first sample moment is also an estimator for the population mean, the first moment. And this one, basically the sample moment is trying to estimate mu to the k from a sample x1 to xn. Now, here's an interesting thing that we're going to see next, which is the definition of central moment. Central moment is the difference, the expected value of the k difference, the k to the power of this thing. Okay, so x minus mu1, we find the difference between individual variables and the first moment, which is the population mean. And we take this is always the first moment, or this is the population mean, as you can see. This is the population central moment, is the deviation of individual items from these and taken to the power k. So in other words, the variance is the second population central moment. So these general moment definitions, we have already know two specific versions of them. Which is the first moment is the mean, second central moment is the variance. Okay, but here is the difference from our estimation for population variance. In order to have an unbiased estimator, remember that we were computing this thing. This was k was 2, and we were dividing it by 1 over n minus 1, right? The equation is right there here on this 2 slides ago. As you can see, this was the estimation for population moment. But this is not the equation that you see here, s squared, is not the second central, sample central moment. So it's a lot of terms. So it's the sample central moment that we are seeing, and this is the second moment that we are seeing here. This is how it's defined. Okay, the second sample moment. It should be central moment. So central is actually left out here. As you can see, it's too many terms. The kth sample central moment is computed as. Yeah, I have a typo here. This is important. Okay, so this should be not sample moment. This is the sample central moment. Okay, otherwise in the previous slide, it's saying the kth sample moment is not about differences. It's just k to the power that. So, right. So kth sample moment is computed as, and kth sample moment is computed. So these are conflicting. So this is the central moment. So I'm missing a term here. So what I was saying was the equation that you see here, which is our estimate for the unbiased estimate for sample variance, is not the second sample central moment or sample second central moment. All right. So there's a difference, as you can see. They will be a little bit different. One of them, if you want to have if you want to compute the sample central moment, you divide this by 1 over n. You just do it like the average as you do it for the population, the moment only. Okay, and the central moment, it's also divided by n like this. I think the main reason is that to generalize this, if you're going to have the third power or fourth power, for example, the third sample central moment will be xa minus x bar to the power 3. And in that case, in order to have an unbiased estimator, we'll no longer probably have 1 over n minus 1. So this 1 over n minus 1 thing that we divide may be unique to the second central moment to have an unbiased estimator, but we want to have a general formula here for any moment, and that's why although it contains a little bias, we still may want to divide it by 1 over n. So just take a note of this difference when you're going to, in method of moments, for example, when we are going to use the central moment as our moments to estimate a parameter. If you're using method of moments, you will not be using sample variance. You will be using the second sample central moment, which is divided by 1 over n, if it's the method of moments that we are going to be using. But I mean, don't let these two slides confuse you. They're nothing but just a way to generate equations. And one thing you may ask at this point is that the moments already give us unlimited number of equations already, right? I mean, since you can take this k, you can start from 1, go all the way to infinity. If you have 10 parameters, you can just use the population moments to compute your unknown parameters. Why do we need central moments then? It's just an alternative, another choice that is given to you instead of taking the expected value of the two. If your variable, for example, is a small variable that is fluctuating around 0, taking a lot of powers of it may lose certain precision. If you're just going to use moments, you may just want to limit your order of your moments to small numbers. So central moments just give you a way to come up with another equation by just using k1 or 2. You can find this. Oh, by the way, central moment, we cannot have k is equal to 1, because in that case the expected, in other words, the first sample central moment, or the first central moment, population central moment, is always 0, right? I mean, if you take this power, if you make k 0, this is equal to expected value of x is equal to the first population moment, and subtract from that mu1 if k is equal to 1. We always get 0. That's why we had this squared when we're computing the variance, right? So the central moment starts at 2, the second central moment. But the population second central moment is the variance. So this is the variance, but if you look at the sample moment, it's not the formula has a little difference here. Now, let's see how we can use these. So these central moments, the population moments, as I said, they're just there defined for you to have different equations that are not linearly dependent on each other, which will give you, if you have 4 unknowns, you can get yourself 4 different equations with 4 unknowns, and you can try to solve those. So to estimate, here's a general method of moments algorithm. To estimate k parameters of a distribution, equate the first k population and sample moments and solve a system of k equations and k unknowns. So this general method does not even refer to the central moments, as you can see. Okay, we don't need the central moments to use the method of moments. By just using the population moments, directly the expected value of x, expected value of x squared, expected value of x cubed, expected value of x to the 4. We compute these expected values for the population as an equation, all right? And then the sample moments are computed as numerical values. And this will give us, what I mean is that mu1 to mu k on the left-hand side are going to be analytical solutions which contain your parameters as variables in them, all right? And for example, let me just tell you, try to explain what I mean in more detail. So for example, in alpha is equal to, you can write alpha in terms of your population mean and standard deviation, right? I mean, if the population or mean and variance. Okay, so, or actually it's not alpha. So here, what we already know that for alpha, for example, the gamma distribution, the first population moment, which is the mean, is equal to alpha over lambda. Okay, now what we're going to do is, what is the second population moment? The second population moment is the expected value of x squared. So what we need to do is, we need to come up with an analytical equation here by using the PDF of that gamma distribution. We have to figure out what is the PDF of the gamma distribution has alpha and lambda in it. So we are going to write the PDF fx egg. So this is the PDF of that from minus, so gamma starts from 0, right? So 0 to infinity, and we multiply it with x squared dx. So we need to compute this, and the result of this, so this fx dx here is going to contain parameter related, which contains alpha and lambda in it. And if you solve this analytically, you will come up with equation that contains some alpha and lambda in it with certain in an equation, in a more complicated equation. It's not going to be just 2 alpha lambda, for example. It should be probably linearly independent of this expected value of x. But first, we're going to give ourselves analytically what this second population moment is in terms of alpha and lambda. So we'll have 2 equations on the left-hand side of this, 2 equations on the left-hand side with some alpha and lambda in them. But they're analytical, they don't have anything, they contain nothing known about these alphas and lambdas. Then on the right hand side, by using this sample we collect, we are going to compute these sample moments as numerical values. So M1 will be, after it's computed, it's going to be a number like 3. M2 will be like 5. Okay, so we will compute these things on the right hand side, which will allow us to have k unknowns, a system of equations with k unknowns and k equations, and we'll solve those. So let's go ahead and take a look at this interesting family of distributions that we haven't seen before, the Pareto distribution. This is example 9.5 from the book, and after this I think we'll finish method of moments, and that was my goal today. So if you look at the cumulative distribution function of the Pareto distribution, and the mean and standard deviation is not given to us here, right? It has two parameters, sigma and theta. Okay, so theta and sigma are its two parameters. This is the cumulative distribution function. So it's defined for values where x is greater than sigma. Okay, so we'll need to integrate this from sigma to infinity. So the domain of this is from sigma to infinity. It has two parameters. So how can we find, when we have a sample, how can we solve for these? First of all, instead of trying to find an equation for mean and standard deviation, mean and variance, we just, in method of moments, we first find the equations for the first population moments, mu1 and mu2. And then after we have those, M1 and M2, based on our sample, we are going to compute M1 and M2, the sample moment, by using our sample. For example, how do you compute M1 from the sample? It's just the sample's average. Whatever sample values you may have collected 15 data points, the average of those 15 data points will be M1. What is going to be M2? You take the squares of each of those individual data points, you sum them, you take their average, that's your M2. So M1 and M2 are really easy to compute. It's just like, as I said, taking the squares, summing them up, and taking the average. Now, here is the analytical thing that we need to do. We need to find the population moments in terms of theta and sigma. So in order to do that, in order to find the expected value of x, we need the PDF, probability density function. So we first take the derivative of this. When you take the derivative of the CDF with respect to x, this is your PDF function. Looks complicated. And then what you can rearrange this, and it becomes this theta, sigma to the power theta. These are just constants, as you can see. So x to the power some number, x to the power minus theta minus 1. So you multiply that with x and take the integral from sigma to, because it's defined after for values of x greater than sigma. So from sigma to infinity, you take the derivative. You can use Wolfram alpha to do that if you want to do, or if you don't want to do it on paper. And the analytical solution will turn out to be theta times sigma divided by theta minus 1. So this is, as you can see, the population first moment. It's also the expected value. It's the mean is, in terms of this theta, sigma, and is this equation. Okay, now let's take a look at mu square. The only thing you need to do is, you already know fx. Now multiply this fx, the PDF of this function, this time with x square, and again integrate it from sigma to theta. When you take it, when you do that, you see that we have a different equation for the second population moment. Sigma is squared, but theta is not squared. So these two equations are not linearly dependent on each other. They're really different equations. So that's really important. I mean, in order to have k unknowns and k equations, no two of those equations should be linearly dependent on each other, because in that case you will have less number of equations than unknowns. So this method of moments, taking the expected value of x squared will give us a way to come up with an equation of these two variables which are not linearly dependent on each other. Okay, so this is our second thing. So all we need to do is equate this to M1, equate this to M2, and this is also like an analytical solution that we show on this slide. Okay, so how can you find what theta is in terms of M1 and M2? If this was treating this as just a constant computed value, you can write sigma in terms of this one, for example, or sigma is equal to M1. So let's try to do that here. Let me write it here. Let me change the pen. So I cannot change the pen. The annotate really is not working. It's not allowing me to change the pen. Or should I change this one? No. I want to change the pen, but it doesn't. Cisco WebEx does not want my left mouse click. Anyway, so I can do it the other way around. Let me just copy this quickly. All right, now let's get to a new slide here. All right, so what I mean is that from here we can write sigma is equal to m1 theta minus 1 divided by theta. Okay, so this is what sigma is. So from here you can replace theta square with this thing. Okay, so theta, and then take square this thing, m1 square, and then you can solve theta in terms of m1 and m2. The only unknown will be theta in that equation. I mean, if you just take sigma and take the square of this thing and replace it in this equation, you will have one equation with unknown and it will have m1, m2 in it. So you can write your theta in terms of m1 and m2. So this is actually exactly what they did. Theta becomes the square root of m2 divided by m2 minus m1 squared plus 1. So they are actually, this one is found by solving this equation, putting, let's actually just do that. So m1 theta 1, sorry, not theta 1, theta minus 1 divided by theta squared divided by theta minus 2 is equal to m2. So all you need to do is just make these multiplications. For example, so this is theta divided by there's theta squared, right? So these are actually going to cancel. After you take the square, the square of this thing is going to be cancelled. What you're going to have is m1 square theta square minus 2 theta plus 1 divided by theta minus 2. So you just need to do the math, just some additions and subtractions, putting these things here and there to find what theta is. And at the end, it will come up with this value you see here, with this equation you see here. So M2 and M1, these will be numerical values we compute from the sample. M1 is just the average, sample average. M2 is you take the squares of your data points and average them. That's what M2 is. And sigma then in terms of M1 and theta. So this algorithm also tells you that you have to first compute theta first. After you compute theta, you just plug in. It's easier to just plug in theta that you have computed here, multiply it with M1, and you get yourself the sigma. And these are called the method of moments estimator, because we have used the first and second population moments and the sample moments to estimate what this theta and sigma is. All right, so that's it for the method of moments. And in general, if you have more than k, or even if you have just one variable, for example, for Poisson, you can use the first population moment, which is just the mean. So in other words, x bar is equal to lambda bar in method of moments for Poisson distribution. Use the first population moment. But in general, if you have larger or more number of parameters in a distribution that are unknown, you just take the first k population moments, compute their equations analytically, and then numerically you find sample from the collected sample, you compute the numerical sample moments, and then you equate these to each other. You solve for those k unknowns. All right, so that's it for method of moments. We are going to continue with method of maximum likelihood on Thursday, and it also requires taking derivatives. The analytical computation of method of maximum likelihood may take some calculus too. So, but we are going to see a simple example and just know what this method is about. All right, that's it from me for today. I'll stop recording now.